Alright, this is video 3 for the momentum unit. So in this one we're going to look at collisions. The way we classify collisions is based on what happens to the kinetic energy of the colliding objects. You have some experience with this. If you take a ball and drop it, it does not rebound to the same height. What that means then is that the kinetic energy just after the collision with the floor is less than the kinetic energy of the ball before it hit the floor. So, for our knowledge then, in a collision between objects, linear momentum is conserved. In an elastic collision, the kinetic energy is the same as before, as it is after. So, elastic collisions. These are collisions in which both momentum and kinetic energy are conserved. So what we would say is that we have our conservation of momentum, but we also have our conservation of kinetic energy, which we say the kinetic energy, the initial kinetic energy of object 1 plus the initial kinetic energy of object 2 equals the final kinetic energy of object 1 plus the final kinetic energy of object 2. So that's for an elastic collision. So if we drop a ball and if it rebounded to the same exact height that we released it, then we would say that that ball had an elastic collision with the floor. Obviously that's not exactly accurate. We have cases where there are some collisions that are pretty close to being elastic. Playing pool, for example, when the balls hit each other when you're playing a game of pool. That is pretty close to an elastic collision. A Newton's cradle, where you have those 5 steel ball bearings and you pull back one and it hits the rest of them and it knocks the last one off and it kind of ticks back and forth. That is pretty close to an elastic collision. So collisions between really dense material at low speeds tend to be pretty close to being elastic. An inelastic collision then would be a collision where the momentum is conserved, but we see less kinetic energy in the system after the collision. Energy cannot be destroyed, so we have to ask, where did that missing kinetic energy go? Typically it's thermal. When two objects collide, their atoms push against each other. There's a little bit of internal friction. So when you have two objects that are colliding, generally what happens is that the objects themselves warm up from internal friction with their own atoms. So that's what happens. So in an inelastic collision, all we have is the conservation of momentum. Now, when two objects are colliding and that collision results in the two objects being stuck together, we say the collision is perfectly inelastic. Then the decrease in kinetic energy from a perfectly inelastic collision is as large as it possibly can be. That's not to say that we're losing all kinetic energy. It's just that the decrease in kinetic energy is as large as we can get. Now, this next statement is very, very important. No matter what type of collision, momentum is always conserved. It doesn't matter if it's elastic, inelastic, or perfectly inelastic. Momentum will always be conserved. Now, the velocity of the center of mass of a system cannot be changed by an interaction within the system. That's very important. So if we take a look at the solar system, our solar system is in orbit around the galactic cluster at the center of the Milky Way. Just because there are asteroids colliding inside of our solar system, that does not affect the speed of our solar system about that galactic center. So the center of mass of a system depends on the masses and positions of the objects in the system. When we have an isolated system, the velocity of the center of mass does not change. So that's very important right there. In an isolated system, the velocity of the center of mass does not change. When objects in a system collide, the velocity of the center of mass of the system will not change unless an external force is exerted on the system. So that's a very important statement right there. When we take a look at a system, if there's nothing outside acting on that system, it doesn't matter how the things interact inside, it does not change the velocity. So another example of this might be if you are running, your body is a system. Let's say you have some atoms colliding inside of your body. That does not change your overall velocity. Another example, if you're in a car, reaching around inside the car, moving things about, does not change the overall velocity of the center mass of the car. Now, there is some more weird examples of this, especially in binary star systems, where we see that the system is wobbling a little bit. But we'll take a look at that, and we'll see how the center mass of that, how that doesn't actually change. All right, this is going to conclude our unit on momentum.